Hi, welcome to the Abbey Road Observatory. I'm your host, Jim, the filter guy. I'm in my lab today doing some filter testing, specifically on this batch of new filters that I received from Svbony. Now, I have tested their filters in the past. I've tested the SV240, which is good for taking images of galaxies when you're in light polluted conditions. It has like an IR pass band. I've tested that. SV220 7 nanometer wide. It's a dual band filter, good for emission nebulae, again under light polluted skies. And then the very recently released SV220 3 nanometer filter, which I wrote a test report on just very recently. So I already have data on those three, and now I'm going to add to that test data from these 6 filters, which includes their sulfur, hydrogen, oxygen 5 nanometer narrowband filter set. So test those. They have a second generation SV220 3 nanometer. They took some of my suggestions in an attempt to improve both the performance at fast F ratios and also try to reduce the presence of halos. So I've got that to test. I've got another, it's branded SV220 again, but this is a oxygen 3 sulfur 2 filter that you could put with one of the H-alpha 03 filters to do Hubble palette imaging with your color camera. So they have one of those. Going to test that. And then finally their IR pass filter, which is great for imaging the moon or capturing steadier luminous data for planets. So I'm going to be testing that as well. So I'm going to start out with doing some bench testing. I have my spectrometer set up here. You can see the output coming from my USB-based spectrometer. And this is my light source that I use here. It has a mechanism that allows me to tilt the filter at various angles. That's how I collect all my spectrum data for the filters. After that, I intend to move over to this rig here, which is a bright halogen bulb that shines through a filter using just a simple filter drawer. I'll hook my my lead up here. It's optical fiber lead into here. I'll use that to attempt to measure the off-band blocking of each of these filters, which I've found in past testing to be directly related to how prominent the filter produces halos around bright stars. Better blocking, less halos. So that's the plan for the bench testing. Weather has been terrible here for the last 2 months, so the chance of getting some image data is not very good for at least another couple of weeks. But when the opportunity comes to collect image data, I'll add that as well. So if you would like to see how this all turns out, stay tuned, and the rest of this video will present the results of all of my bench testing. All right. By the way, if you are enjoying the videos that I prepare here on YouTube about filters and other astronomy related topics, maybe you'd like to take a sec to click the like button down below. And if you want to stay up on everything that the Abbey Road Observatory is doing, maybe you'd like to subscribe to my channel. It'd be great. Alright, let's get on with the results of my bench testing of Svbony astronomical filters.
Welcome to today's video, where I will be presenting the results of my testing, a selection of Svbony's astrophotography filters. I've had these filters for a few months now, but observing conditions have been poor this winter, and so it has taken until now for me to complete all of my testing. I apologize to those who have been waiting for this review since they saw the announcement it was coming over a month ago. Hopefully by the end of this video you will feel that your patience has been rewarded. Let's begin with a bit about Svbony. They are a Chinese company based in Hong Kong that was founded in 2009. They specialize in supplying budget-friendly consumer optics, such as telescopes, spotting scopes, binoculars, etc. Unlike a number of other astronomy equipment suppliers, they do not simply rebrand products manufactured by somebody else. They design and manufacture their own products. Included in their list of astronomy-related products are an assortment of optical filters for use in astrophotography. That is the topic of this video, where I attempt to answer the question, how do Svbony filters compare with their competitors? Specifically, I have tested 9 different filters in 5 categories. The list includes an IR pass filter, the SV183, a pair of SV220 7nm multi-narrowband filters, one with pass bands at oxygen 3 and hydrogen alpha, and the other with bands at oxygen 3 and sulfur 2. Included in the list are 2 versions of the SV220 3nm multi-narrowband filter, a sample of the first released version of the filter, which I call Rev 0, and a newer version, Rev 1, that is reported to implement recommendations I made in a test report from last fall. The SV227 sulfur hydrogen oxygen 5nm narrowband filter set is also included in this test. And finally, the multi-purpose multi-narrowband filter, the SV240. The prices noted in this table are in US dollars and are for the 2-inch filter size unless otherwise noted. For each filter category, I have selected from my library a number of filter offerings from competing manufacturers, as summarized here. Not included in this test is the multi-broadband SV260, which is very similar to the Optolong L Pro or the OIII-S LPS P3, which are not really suitable for use under the heavily light-polluted conditions that I have here in central Ottawa, Canada. Except for the SV220 7nm OIII-Ha and the SV240, all of the Svbony filter samples used in this test have been provided to me by Svbony. Other than the free filter samples, I have not been compensated in any way for performing this test, nor does Svbony have any say in what results I share with the public. For this filter test, I applied my now well-established standard filter test protocol, beginning with a general inspection of the filters, including their packaging and documentation. That is followed by a rigorous measurement of filter spectra using a benchtop spectrometer. I am able to measure spectra from 380 to 1100 nanometers with a 0.5 nanometer resolution. My test rig also allows me to orient the filter at angles ranging from 0 to 20 degrees relative to the light path. The final source of test data that I collect is from imaging multiple deep sky targets from my urban backyard, which is at Bortle 9+, a naked eye limiting magnitude of around plus 2.9. For this particular test, I used 2 different telescopes, a William Optics FLT98 at its native f6.3, and an ASCAR FMA 230 at its native f4.6. 3 different cameras were used for this test, a one-shot color ASI 533 MC Pro, a monochrome ASI 533 MM Pro, and a monochrome ASI 183 MM Pro. The data collected is used to evaluate a number of performance parameters for the filters, including f-ratio sensitivity, contrast increase, signal-to-noise ratio, star halos, and ultimately cost effectiveness. This is a photo of my spectrum measurement setup. Starting on the left side of the image, I have a regulated DC power supply driving a custom-built flat spectrum light source which shines through the filter under test to a collimating lens. This lens connects to an optical fiber test lead, which is in turn connected to my spectrometer, an Ocean Optics USB 4000. This device connects to my laptop via a USB connection. I use the free OIII-Ha software for my data collection. This photo is of my imaging setup on the first night of my data gathering. The two telescopes, the FLT98 and FMA230, are visible in the upper left. I use filter drawers so that I can quickly switch from one filter to the next. The scopes are driven by a pier-mounted Skywatcher EQ8 Pro. You can see I have a heat lamp pointed at the mount's base in an attempt to alleviate the cold somewhat. For my setup, I have a laptop outside that runs the mount and cameras, which I then connect to from inside the house using VNC. My laptop is hiding under a fleece jacket in this photo, as it is also trying to stay warm. This particular evening was the first clear night we'd had in several months, so I was not about to let it pass by, even though it was minus 25 degrees Celsius. The second test night was even colder, at minus 28 Celsius. Oh, the hardships an amateur astronomer must endure for their hobby. At the start of this particular test program, I had planned on measuring off-band blocking. A filter's off-band blocking is a good indicator for whether or not it will produce halos around bright stars. This is an image of the test setup I used in my attempt to measure this parameter. I had a halogen light bulb shining down the inside of an assembly of 2-inch extension tubes, to which was attached a filter drawer. On the opposite side of the filter drawer was my optical fiber test lead, connecting then to the USB 4000, operated again using the OIII-Ha software from my laptop. Unfortunately, my setup had too much electronic noise, light leaks, and CCD sensor bloom. That is, the tendency of saturated sensor pixels to overflow electrons into neighboring pixels. The largest off-band blocking value I could reliably measure was around OD 3.5. This is not enough to evaluate modern astronomy filters, which can have off-band blocking better than OD 5. Moving on now to the results of my testing, starting with the general inspection. I found all of the Svbony filters to be well constructed and packaged. Each filter comes inside a rigid foam-lined case, which is then packaged in a colorful outer box. Inside each box there is also a small paper printout of the filter spectrum. You can see here in the photo. The filters also come with a self-adhesive protective film on each side to keep the filter nice and clean. I was happy to see that Svbony's choice to use a rugged plastic case with a firm clasp. Some other filter suppliers like Antlia use cases that are oversized and don't close firmly, making them very impractical. The only thing I did not like about Svbony's packaging is the labeling on the case and outer box. The text is too small to read for aging eyes, and the descriptions are ambiguous. For example, all 3 of the SV227 filters have the same description, simply stating narrowband filter. Now, let's work our way through the performance results for each filter category, starting with the IR pass. The main use for IR pass filters is imaging galaxies when under heavy light pollution, or for settling down the seeing when imaging the moon or planets. They are normally high-pass or very broad-band pass filters, so optics F ratio does not have any effect on these filters. The spectrum measured for the SV183 and II comparison filters are shown in this plot on the left. The SV183, shown with the red curve, has a spectrum very similar to the Baader filter, which is shown in green. Based on the measured spectrum of these three filters, I have made a prediction of filter performance when imaging galaxies under varying levels of light pollution. The horizontal axis is a prediction of the relative signal-to-noise ratio, where a value of 1 means the same as with no filter. The vertical axis is a prediction of deep sky object contrast increase relative to no filter. The higher and more to the right a data point is on this plot, the better the performance. The numbers noted in each data point correspond to the light pollution level in terms of naked eye limiting magnitude. A NELM of plus 2.9 corresponds to the light pollution level of my own urban backyard. Based on my predictions, the SV183 filter should perform pretty much identical to the Baader IR pass filter. Because of the time of year, I was not able to collect any image data on a galaxy during this test program. These images were captured from a previous test back in March of 2021, before the SV183 was available. They give an idea of the impact an IR pass filter has when imaging a galaxy from a Bortle 9 Plus location. Something I was able to image using the IR pass filters for this test was the moon. These are stacks of the best 150 frames from 1000, stacked in auto-stackert and sharpened in IM PPG. There is a clear improvement in sharpness and detail visible from using the IR pass filter over no filter. The SV183 performs again pretty much the same as the Baader filter. The astronomic filter, however, has a bit of an edge over the other two for this particular application. If you are interested in learning more about imaging using infrared light, you should check out my video, Seeing Beyond the Visible, a link to which is in the comments below. The next filter category to discuss is 7 nanometer wide multi-narrowband filters. From the measured spectra of these filters, it is clear that the Svbony pair is positioned to compete directly with the Optolong L2 dual combo. The Svbony and respective Optolong filter have very similar spectra. The exception is my sample of the SV220-03 H-alpha filter. It has an H-alpha pass band shifted slightly to the left. I don't know if this shift has been corrected in more recent batches of this filter. Having similar spectra, it is no surprise that these filters all have very similar sensitivity to optics F ratio. The shifted H-alpha band hurts the one SV220 filter, but otherwise these filters all perform well down to at least f2.8. My prediction of filter performance is shown here using the same format that we saw earlier. The Svbony filters are predicted to perform similar to the Optolong equivalents, with the exception of the SV220-03 H-alpha filter, which again is showing a performance deficit due to the shifted band center wavelength. Note how, unlike what we saw earlier for IR pass filters on galaxies, multi-narrowband filters improve nebula contrast and SNR regardless of the light pollution level. This is a sample of the images I captured for this test, in this case of the Rosette Nebula. They are all stacks of 20-second sub-exposures for a total exposure of 5 minutes, collected using Sharp Cap and then stretched identically using a macro. The Svbony and Optolong filters appear to produce images that are very similar in appearance. Worth noting is that the stars look larger in my Svbony filter images. That is not due to the filters. It is due to the focus of my test setup drifting rapidly as the ambient temperature plummeted during my testing. Because the visible differences between these images are small, I have extracted measurements of contrast increase using the image analysis tool ImageJ. The results are plotted here in terms of how the measured values compare to the predictions. Data points below the diagonal line are worse than predicted, and those above the line are better than predicted. To improve the quality of the comparison, I have added data points collected with these filters from previous testing, performed in the fall of 2025. Based on these measurements, the filters all seem to perform pretty much as predicted, with the exception of the SV183 filter, which, oddly, performed slightly better than predicted. More like the L Extreme filter, in fact. The next filter category to compare is 3-nanometer multi-narrowband filters. As with the 7-nanometer filters, the 3-nanometer filters have spectra that are very similar to each other. Of note is the change in spectra between the Rev 0 and Rev 1 Svbony filter. Svbony has successfully moved their filter passbands a bit to the right, so as to improve F-ratio sensitivity. As we can see on this plot, comparing the red line to the green line, there is definitely an improvement there. This change was made at the cost of a slight reduction in peak transmission and slightly wider full-width half maximum, the impact of which we will see in a moment. The predicted performance of the Svbony and other comparison filters is all very similar to each other. My predictions suggest a slight improvement in performance going from Rev 0 to Rev 1 of the Svbony filter, but that will need to be confirmed from the imaging data that we will see next. Based on this set of images, a subset of all those collected during my testing, there is indeed a very small difference visible in the performance of these filters. They are all very similar. When I plot the contrast increase measured from each of the images, the similarity in performance is even more evident. I have again included additional data from my fall 2025 testing to improve the quality of the comparison. The filters all perform on average the same as predicted. The exception is the SV220 Rev 1 filter, which was found to perform consistently below predictions, but consistent with the observations made from the filter's spectrum compared to that of the Rev 0. The next filter category to cover is narrow-band sulfur, hydrogen, and oxygen, or SHO. I don't have another 5-nanometer wide set to compare with the Svbony filters, so I have instead compared them with my 3-nanometer Optolong set. The difference in bandwidth is pretty obvious when we compare each filter's spectrum. Also interesting is how much higher the peak transmission is of the Svbony filters compared to the Optolong filters. The bandwidth has a large impact on F-ratio sensitivity. with the wider Svbony filters having a greatly reduced sensitivity compared to the Optolong filters. Take, for example, the sulfur 2 filters, plotted with the red curves. The Optolong filter never exceeds about 75% transmission, and is below 50% transmission on optics faster than f4. The Svbony filter, in contrast, has over 90% transmission for f5 and slower, and does not get to 50% transmission until around f2.8. Looking now at my predictions of filter performance, the Optolong filters are predicted to deliver a better contrast increase, which is expected because they are significantly narrower, 3 nanometers versus 5. However, for the OIII and S2 filters, the two brands are predicted to deliver roughly the same SNR. The wider pass bands of the Svbony filters are being compensated for by them having higher peak transmission than the Optolong filters. By the way, you may have noticed that there is a big difference in performance between the sulfur 2, oxygen 3, and H-alpha filters. This is because of the difference in the amount of emission of each of these wavelengths from a typical emission nebula. By far, the most light emission is coming from hydrogen alpha, followed by oxygen 3, and then least of all, by a large margin, is sulfur 2. When we have a look at the comparison images, they seem to confirm the predictions that the Svbony filters are performing pretty well against the narrower Optolong filters. Looking at the measured contrast from each image shows that the actual filter performance is pretty much bang on the predictions. If anything, the Svbony S2 and H-alpha filters are performing a little bit better than predicted. The last filter category to compare is multipurpose multi-narrowband filters. These filters have an extra pass band in the near-infrared range that gives them good performance on both nebulae and galaxies from light-polluted locations. These filters also tend to have fairly wide pass bands, which result in them having very little sensitivity to optics f-ratio. Based on my spectrum measurements for the three filters being compared, the SV240 is very similar to the OIII-SII GNB. On emission nebulae, the SV240 is predicted to have an advantage over the other two filters in the comparison. Note that I've included two versions of the Antlia filter on this plot. The version 2 of this filter has a narrower IR passband than version 1. It is version 1, however, that I have a sample of. On galaxies, the SV240 is predicted to have an identical performance to the GNB. Not surprising, considering how similar their spectra are to each other. Comparing images taken with these three filters of the Rosette Nebula, they appear to deliver very similar performance. Note that again, I had some focus issues for the SV240 and Antlia filter because of the cold weather. Looking now at the plot of contrast measured from my test images, including images captured in January 2025 from a previous test, we see that the filters are all performing as predicted with the exception of the Antlia filter, which is performing better than predicted. On average, the contrast delivered by these filters is all roughly the same. I did not have any conveniently located galaxies to image for this recent test program, but I do already have data from these filters from a test I did in January 2025. The improvement in image detail that using a filter brings is rather subtle, compared to the no-filter image, but the improvement is visible. Plotting the contrast increase measured from this image confirms that the SV240 and G&B are performing similar to each other on galaxies, and pretty much as predicted. The Antlia filter was observed again to be performing better than predicted. The last observation to make from the collected image data is each filter's propensity for halos around bright stars. Displayed here is a zoomed-in view of the area around the star Alnitak, a bright and very hot young star in Orion's belt. This star is notorious for causing halos. I have ranked each filter tested for halo visibility, the scale ranging from 0, for no halo visible, up to 3, which is a halo so bright that even the second-order halo is visible. The image in the upper left from the DGM NPB improved filter is a good example of a level 3 halo. I found all the IR pass filters tested to have a very slight halo, so level 1. The SV220 7nm OIII-Ha filter has a level 2 halo, and the OIII-SII filter a level 1 halo. In contrast, the Optolong L2 dual combo filters have a level 1 and level 0 halo, respectively. The first version of the 3nm SV220 has a level 2 halo, but the Rev 1 filter has a much better level 1 halo. In comparison, the Optolong L Ultimate filter also has a level 2 halo, and the Antlia ALPT 3nm has a level 1 halo. So the Svbony filters are very comparable to those other brands. Amongst the narrowband SHO filters, all of the H-alpha and S2 filters were found to have no halos, but the O3 filters did. A level 2 halo for the Svbony filter and a level 1 for the Optolong filter. The SV240 was found to have a prominent level 2 halo. However, the other two filters in this category were worse, with a level 3 halo. The last piece of information to extract from my test data is a measure of the cost-effectiveness of the filters. I am using as a metric the cost of the filter divided by its predicted SNR, the calculated values of which are summarized in this table. The Svbony filters very clearly deliver a lower cost per unit SNR. The largest disparity was found for the SV183 and the SV227 filter set, which are less than 1/4 the cost of the comparison filters. That concludes my review of Svbony's astrophotography filters. I have presented a lot of data on these filters, but my results boil down to the following conclusions. 1. The SV183 is a very inexpensive alternative to the Baader IR pass and other similar IR pass filters, giving virtually identical performance for less than 1/4 the price. 2. The SV220 7nm filter pair is a competitive option to the Optolong L2 dual combo. They give similar performance at about half the price. The only thing to note is that the Svbony filters have halos while the Optolong filters don't. It is worth noting that Optolong has only recently started revising their filters to reduce halos. So any L-Extreme filters more than a few months old are probably first generation, which do have prominent halos. Conclusion number 3. The SV220 3nm filter is a competitive option to the other brands of 3nm multi-narrowband filter. It delivers very similar performance, and Svbony has recently introduced changes to improve halos and f-ratio sensitivity. Number 4. The SV227 5nm SHO filter set is a very inexpensive alternative to other SHO sets. They give good performance, even relative to filters with a narrower bandpass. The only drawback being a prominent halo with the O3 filter. And finally, conclusion number 5. The SV240 filter is a competitive option to the OIII-S GNB or other multi-purpose multi-narrowband filters. It delivers very similar performance and is slightly better with halo generation. Well, that's it. I hope you have found this video useful. Feel free to leave any questions you might have in the comment section below, or alternatively, you can message me directly using the email address in my channel description. If you would like to review the results of my Svbony filter testing in more detail, including all of the images that were captured during the testing, you can download my test report from ResearchGate using the link shown here. If you have enjoyed this video, please take a moment to click like. If you would like to stay connected to everything the Abbey Road Observatory is up to, please subscribe to my channel. Thanks for watching. This is Jim the Filter Guy wishing everyone clear skies.